Hey guys, here's another video on stoichiometry, this one relating moles and mass. Previous videos started out with just mole-mole ratios, and now we're going to make it a little more difficult. Let's say you have ammonia, NH3, also known as nitrogen trihydride, and that ammonia can decompose into nitrogen gas and hydrogen gas. When you look at this, it is not balanced yet, so we have to do some balancing to get this to work. And what we're going to notice is that, well, the nitrogens increase by 1. You have 1 nitrogen in ammonia and 2 on the right, and the hydrogens decrease. So I think we're going to try balancing this by putting a 2 in front of the ammonia and then a 3 in front of the hydrogen gas. Therefore, we have 2 nitrogens on both sides and 6 hydrogens. Now that we've got that done, you might have to answer a question like, well, if I have 50 grams of ammonia that decomposes, how many grams of each of these products do I get? How many grams of nitrogen and how many grams of hydrogen are produced? We can figure those questions out using stoichiometry and mole ratios. First thing you need to do is convert our starting compound, ammonia, into moles, because while we can look at the mole ratio of 2 ammonias to 1 nitrogen to 3 hydrogens, these ratios do not work for mass, but only for moles or number of atoms. Moles, of course, as we've talked about, are proportional to the number of atoms or molecules. Mass is not. So we must start by converting our 50 grams of ammonia into moles. In order to do this, we of course have to add up the mass of 1 nitrogen and 3 hydrogens using our periodic table. And when we do that, what we come up with is a mass of 17.04 grams per mole for ammonia. Notice that the grams follow the diagonal rule and cancel, leaving us with moles of ammonia. And the first question I guess we want to answer is how many grams of nitrogen are produced? Well, we have to relate the moles of ammonia to nitrogen. And here's where we look at the mole ratio. Because there's no coefficient in front of nitrogen, 1 mole of nitrogen is made for every 2 moles of ammonia. And we know that ratio because this right here is implied to be a 1, and this here is a 2. Now our moles of ammonia cancel, and we're left with moles of nitrogen gas. The final step, then, is to convert the moles of nitrogen gas to grams of nitrogen gas. Just like before, we must use the molar mass number from the periodic table, just like we used for the ammonia. And in this case, we're adding up the masses of 2 nitrogens. If each nitrogen weighs 14.01, we have a mass of 28.02 grams for the nitrogen gas. To get our final answer, we start by typing 50 into our calculator, 50.0. We divide that by 17.04, because 17.04 is on the bottom of our table. We divide that by 2, and then we multiply by 28.02. And when I look at the number of sig figs, I start out with 3 sig figs for the grams of ammonia. We have 4 for the molar mass of ammonia. And again, we never round our sig figs down because of the mole ratio. Those numbers there could be written with infinite numbers of accuracy or zeros after them. So we're going to round our answer down to 3 sig figs because we have 3 here, 4 here, and 4 here. That gives us a total of 41.13 sig fig grams of nitrogen gas produced. The next question we want to answer is how many grams of hydrogen gas are made? Well, in order to do that, we're going to do a similar calculation, but instead of using nitrogen gas as our final answer, we're going to look for hydrogen gas. We start out in both cases with the same mass. This was the same scenario. We start out with 50 grams of ammonia. We're going to convert our grams of ammonia to moles of ammonia. We're going to convert the moles of ammonia to moles of hydrogen gas. And then in the final step, we are going to convert the moles of hydrogen to grams of hydrogen. Again, I often like doing it this way, where we put the units in first, because then I can really see where I'm going. I can plot out my course and make sure that I'm not missing a step. Putting in the numbers last. Here we need to fill in the molar mass of ammonia. Well, we've already done that in the previous calculation. Ammonia weighs 17.04 grams per mole. And we want to look at now the moles of H2 versus NH3. I'm going to scroll up a second and we're going to look and see 3 moles of hydrogen gas are made for every 2 moles of ammonia consumed. 3 moles of hydrogen gas for every 2 moles of ammonia. And then lastly, we have to fill in the molar mass of H2. Each hydrogen weighs 1.01, so 2 of them would weigh 2.02. Our final answer then is achieved by starting with the number 50, dividing by 17.04, multiplying by 3, dividing by 2, and multiplying by 2.02. I take a look to see how many significant figures I'm going to round down to. I have 3 here, 4 here, 3 here, always ignoring the mole ratios. Those do not count when rounding down. We know these to infinite numbers of significance or confidence. So rounding to 3 sig figs, I get 8.89 grams of hydrogen gas. So just to review, because the ammonia was the starting place for both of these, to answer both of these questions, we started out with 50 grams of ammonia in converting those to moles. So the first 2 steps in our calculations are the same. Where it starts to differ, though, is what are we looking for? Well, in the first question, we were looking for nitrogen, so we used the mole ratio of 1 to 2. And in the second question, we were looking for hydrogen. And of course, it's also going to differ in the last step, the molar masses of each. Something interesting to note, if we add together 41.1 and 8.89, we get a number 49.99. That number, of course, is very, very close to 50. Because of, small rounding issues, that number is not exactly 50. It's 49.99. However, discounting the rounding, what we notice is that the mass of the products added up is 50, and the mass of our starting reactant is 50. This is an example of how the law of conservation of matter comes into play. You cannot produce more products in grams than you consume in reactants. Another way of thinking about this is mass is conserved. The mass of the products added up equals the mass of the reactants added up. In this case, because we only had one reactant, the mass of the products needs to add up to that one reactant's mass. And that is an example of mole mass relationships.